Hello, everyone. This is number 5 lecture on quantum mechanics. We are now in the chapter 2, time-independent Schrödinger equation. So first, we're going to talk about stationary states. So here's a question. How do you get psi in the first place? From this Schrödinger equation, let's assume that this potential term V has no t dependence, which means that it has no time dependence. And in that case, we can attack this equation so that we get the solution eventually. We have the technique, namely separation of variables. So let psi be the product of this psi x and phi t. Here psi x is a only function of x, and phi t is a function of only variable t. So when we plug in, we get eventually this form, and left hand side is a function of t and right hand side is a function of x, so that the two sides are equal when both sides are in the constant. So let the constant be e. So we get this I ha bar phi prime divided by phi equal e, and this e equals to this. And now first we've got the 1 PDE, and by using this technique we've got the 2 ODE, which means ordinary differential equation, which is very more easy to solve than used when it comes to the notion of the partial differential equation. So the first equation is very easy to solve, and we get directly this differential equation. And here, the second equation, we call this equation, since it's very important, as time-independent Schrödinger equation, since there are no time term, right? So it's better to remember this time-independent Schrödinger equation. And here, again, the Hamiltonian operator term here. So h psi equals to e psi. Here psi is not the original psi. The original psi was the function of two variables, x and t. But here psi is a function of x. So there is no time dependence in this psi. When you solve the time variable equation, which means the ordinary differential equation about this phi, we get this solution. So phi was the exponential of minus I ha bar, which means minus I divided by ha bar, e t. So we call this as a time wiggling term. Time wiggling term. Since this is as t goes on, this phi wiggle like that. So now we have to attack this problem, we have to specify this V potential. And in most of cases, the potential is given by the problem. So here is some notes. Properties of solution of time-independent Schrödinger equation psi. So first, the solution is stationary states, which means psi xt equals to psi x exponential minus I divided by ha bar et, which is of the form this time-independent solution of Schrödinger equation psi x produced by this time wiggling term exponential minus I over ha bar et. So actually, this psi original solution of the Schrödinger equation has time independence. However, its probability density, which can be calculated by the simple conjugate method, has no time dependence, as you can see here. So any quantity has no time dependence when it comes to the expectation value. Since the expectation value is by definition calculated by this sandwich method, here Q living in this bread guys, integral psi conjugate and psi dx, and we know that this psi is of the form psi x and phi t. And the time wiggling phi t is cancelled out because they were conjugate and exponential. The product of exponential is exponential of a plus, So the conclusion is any quantity's expectation value has no time dependence. Fairly easy. So every expectation value is constant in time when V potential is given as no time dependence potential. And second, psi, state of the definite total energy E in classical mechanics, Hamiltonian HXP, what was that? So there are many stories about this Hamiltonian, but we can roughly think this Hamiltonian as the total energy of the system. So p squared divided by 2m plus 3x. So in quantum mechanics, very similar form. We just plug the operator p in that Hamiltonian equation in classical mechanics, namely Hamiltonian operator h hat equals to minus I haba partial x, which is the momentum operator, squared divided by 2m plus v, and this we got as usual the Hamiltonian operator. Thus, the time-dependent Schrödinger equation becomes this simple form h hat psi e psi, and this is of the form in linear algebra, very famous equation and very famous problem, which is eigenvalue problem, right? So the linear algebra is a core heart of the quantum mechanics. So actually quantum mechanics is based on linear algebra itself. So if you want to attack the quantum mechanics useful or efficiently, you must know about the linear algebra well. And let's check it out. The expectation value of Hamiltonian is simply sandwiched Hamiltonian operator, and then the conclusion is it is equal to this E. And this expectation value of h squared is equal to E squared, which is very intuitive, because the expectation value of total energy is of the form the energy E, which was the constant, right? And also expectation value of Hamiltonian squared is e to the 2. And then this variance of this Hamiltonian, the variance of the total energy of the system is 0, which means that every energy it can take is only unique value E. So there is no difference between the value of h. So E is a definite unique value for a given state psi, more formally, eigenvalue. We'll see that in formalism, chapter 3 in quantum mechanics. And next, the general solution is a linear combination of separable solution. So there's an equation, eigenvalue problem, h hat psi equals to e psi. The solution can be like this: psi 1, psi 2, psi 3, psi 4. And this is some mathematical set of this countable set of this solution psi. So we can denote this guys as this simple set notation, set psi nx. And there's an associated separation constant E1, E2, which means that expectation value of that in the case of Hamiltonian. And there is a associated wave function psi 1, psi 2, psi 3, psi 4. And here psi 1 can be very easily computed by the psi 1, small psi 1, produced by this time wiggling exponential minus I over half bar E1t. So we call these solutions as separable solutions. So in last lecture, we've checked that a linear combination of the psi is also a solution. Generally, the general solution psi is the span of this psi n, which means that all possible linear combination of these psi guys. Easy, fairly easy. And this is so here is also the linear algebra guy here. So linear algebra is so important to study the quantum mechanics. So here's a solving technique. So given is here, potential is given, and psi x1, x0, which means the initial condition is given. We solve the eigenvalue problem h hat psi equals to e psi to get psi, and write the psi x0 as this, and eventually we product the time wiggle factor exponential minus I half bar ent. So simple technique. So here is example. Suppose for a particle psi x0, which means the initial psi, is given by this c1 psi 1x plus c2 psi 2x. So here's a question: find psi xt and the probability density of this particle, and describe the motion. So here psi xt can be written by this simple time wiggle term is added: c1 psi 1x exponential minus I over half bar e1t plus z2 psi 2x exponential minus I half bar e2t. And here they are stationary states, which means when we compute the conjugate and original form, which means that norm squared, they have no time dependence. So here is that. However, the respective term is in the stationary state. The whole guy, this psi guy, has time dependence, as you can see this by this computation. This can be treated as some contradiction, but in quantum mechanics, this case can be awkward by one guy is stationary state and other guys is stationary state, but the sum of the guys are not stationary states. So the probability density has time dependence, so this original psi guy is not stationary. So here is some note: the physical meaning of Cn. So when we compute the norm squared of Cn, it means that probability that a measurement of the energy would return En. Also, probability of getting the particular value En. Since this means the whole probability, namely summation all over the running the n terms, we got the one, right? And the expectation value of h is right here, summation over n equals 1 to infinity, norm squared of Cn En. And this Cn has no time dependence, so Cn squared has no time dependence, and thus expectation value of h has no time dependence. So this means the total energy of system's expectation value has no time dependence is corresponded to the energy conservation. There's no time dependence in total energy. So we can think of this as an analogy. In classical mechanics, there is a energy conservation law, which means that energy has constant value as time goes on, and this is the quantum mechanical version of this energy conservation law. So we're gonna solve two problems as usual. So prove the following, the three theorems. So first theorem is for normalizable solution, so the separation constant E is real value. So here's a very simple technique. So let E equals to E0 plus I gamma, where E0 and gamma is in the real space, and E is in complex space. Then let this psi as psi x exponential minus I over half bar et, blah blah blah, and then we calculate the whole space integral of this term, and the given was normalizable, so this calculation's results should be 1. So from this exponential equals 1 term, we can deduce that the gamma should be 0, which means that E is real value. Linear algebra, in linear algebra, the eigenvalue E must be real. And then next theorem, the time-independent wave function psi can always be taken to be real. So note, this does not mean that every solution of time-independent Schrödinger equation is real. If you get solution in complex plane, the solution can be expressed as a linear combination of solution in R. So at this Schrödinger equation, this psi conjugate also satisfy it just by conjugate the whole equation. Thus, the summation of this psi and psi conjugate also, and I product psi minus psi conjugate are also the solution because they are the form of the linear combination of them. So note that in complex analysis, the real part of this psi can be written as psi plus psi conjugate divided by 2, and imaginary psi can be written as psi minus psi conjugate divided by 2i. So as you can see, the solution, they are a solution in real. So we've verified it. Psi can always be taken to be real if we take this. If Vx, next theorem, if Vx is an even function, then psi can always be taken to be either even or odd. So we have this V minus x is Vx at this Schrödinger equation, Vx, when we change this Vx as V minus x to get this simple equation also, so we can think this psi minus x is also the solution. So as always, we take the summation and we take the subtraction, and there they are also the solution. So here is an even function solution, here is an odd function solution. So when the V is given as even function, psi can be taken to be either even solution or odd solution, as of the form this. The next problem show that if E is greater or equal than this minimum value of Vx for every normalizable solution to this time-independent Schrödinger equation, what is the classical analog to this statement? So as you can see at time-independent Schrödinger equation, we can rearrange this equation like this. So suppose for contradiction we use the prove by contradiction that E is smaller than minimum value of V, then we got this. Calculation is going on. So we get this form. So we know that for psi is greater than 0, psi xx, which means double partial differentiation of this psi, should be greater than 0, which means is like this shape, which cannot be normalized. So concave of graph, and in other case, it's concave down graph. But for the sake of the psi is normalized, the both cases are not the cases. So we've got the contradiction. In either case, psi cannot be converged to 0, so psi square cannot be converged to 0, so not normalized. So here's a contradiction. So by proof by the contradiction, we've got it. Okay. Enjoy the physics. Bye bye.